Amin, and Sumaiya is currently completing her master's in science at St. Francis Xavier University, working with Dr. James Hughes. And she has previously completed a Bachelor of Science in Computer Science at the Chittagong University of Engineering and Technology, and also formerly lectured in computer science and engineering in Bangladesh. And so today she's going to talk about how strategies and techniques from computer science are being used to incorporate specific disease parameters to improve vaccine delivery in her talk. And Sumaiya, I'll hand it over to you. Thank you.
Hello, everyone. Firstly, thank you for giving me the opportunity to talk here. So I'm a master's student in computer science at St. Francis. So currently I'm working with my professor on how using genetic programming to find effective vaccination strategies for any infectious disease. Currently, we are focusing on COVID-19 pandemic because we all know that this COVID-19 has been taken a serious toll on human lives and all of this. But however, our model is developed in such a way that it can be used for any other pandemic in the upcoming days as well. So I'm going to present right now. So the research question that we were focused on, how efficiently we can design a vaccination strategies by taking into consideration the dynamic social network so that the impact of the disease can be decreased, because it is often a burden question. And we also can see that for developing countries, it is often a burden question because the resources or the vaccinations are limited there. So often the health workers and the policymakers are in a dilemma, whom they should vaccinate first, or how efficiently they can organize the vaccination program so that in their particular community, the pandemic might not spread too much. So here we are representing the social network as a graphical representation. So where each node will be represented as an individual, and the connection between them will be considered as the social connection between two individuals. So if we get to know the community structure for any particular community, so we can actually design the vaccination strategy for that particular community. So let us see a quick scenario how this can help. So suppose this is a person who is not getting vaccinated and he is already infected. So he has a connection with the individual who is been vaccinated before he got the disease. So what will happen is this person might have more connections, and each person might have more connections. So as he got the vaccination before he get the disease, so what is this person is potentially safer for his other connections. But on the other hand, what happens if we fail to vaccinate the individual before he get the vaccination diseases? He will be spreading the disease to more connection he is connected, and that person will be connected to more other people, and there is a chance that he will get more people infected. So actually, this is the scenario where we want to come up with a solution so that we will design a vaccination strategy for taking into consideration a particular community structure, so that if any pandemic or infectious disease occurs like the SARS-CoV-2, what will happen is the health worker, they will know whom they should vaccinate first in order to spread the disease so that it might not cause any fatal disease to the community. So actually, we have used simulate the model using a SEIR epidemic model, which is susceptible, exposed, infectious, and recovered model, which is actually quite similar to the SIR model. But the only difference is here, we can see there is a state called exposed. That means that in this state, some people, they will have the disease, but they will not show any symptoms of that, and they will not spread the disease as well. On the other hand, the infectious people will have the disease with all the symptoms and they will spread it. So why we particularly adopt this ACIR model here is because we know that in COVID-19, some people, they have the disease, but they are called asymptotic. They will have the disease, but they will show no symptom. So it is equally important to find those people as well, or else we might fail to vaccinate the people who are potentially dangerous for the community. And what is here is we are implementing a dynamic graph here because as we all know that the social community network or anything which it's not fully static, even though we have some like due to our work or university or schools, we have some static connection, but still we often meet new people and for traveling or some things we meet new people or something. So that's why we are adopting here a dynamic graph, which is a power law cluster graph that will represent the social community in more real way. And what we are doing is we are simulating the model by adding the edges, removing the edges, and we will also select which vertices can have these changes as well. And based on that graph, representation of the graph, we are adapting some graph measures that we will use for finding the effective vaccination strategies. We are using here genetic programming. So what will happen here is we will take calculate those graph measures and will feed it to the model. And what will happen is they will return a function as a Boolean value that will tell us simply whether we should vaccinate one individual or not. So here are all the graph measures that we have been used for our model. They are like static, whole graph measures, extra and local. So here I want to shortly describe that the static measures are those measures that will calculate only once. But the local measures that will be like each simulation when will happen, it will change some calculation in the graph and that will be calculated again and again to find more efficacy. And for implementation of the project, we have used genetic programming to find the strategies using the distributed evolutionary algorithmic Python framework, which is DEEP framework. So actually, we know that genetic programming is a particular form of evolutionary algorithm which adopts the natural selection process and will come up with some best solution. And we know that like this finding effective vaccination strategy, there is no space like silver bullet, like which can be specifically effective because which is might be effective for Canada. This might not be effective for my country like Bangladesh. So genetic programming, this will help us to change the objective of the problem. And also we can, according to our need, we can customize our objective as well. So here are the hyperparameters and the languages we used for our work. And then we run the simulation with the predefined pandemic simulation strategy. We can see here the model settings for the SAIMR model and also for the dynamic graph settings. So after running the simulation, we also perform testing for our work because we wanted to get sure that the generated strategies our model is coming up with, this should be efficient enough. So as we already told, like there is no silver bullet point like for finding effective vaccination strategies. So for our work, we particularly focused on the optimization objective to minimizing the maximum and the total number of infected people. Therefore, like it should be flattening the curve. So what we have done is we have performed 100 evolutionary search both on the base and the static and the dynamic graphs. And with each candidate solution, we applied that to 50 different power law cluster graphs because we wanted to be sure that the strategies we are coming up with are not particularly efficient for only one graph. It should be capable of dealing with any kind of graphs because all the community structures is different from one to another. And then from each from base and dynamic strategies, we took the 6 of each strategies we have taken. So in total, 12 strategies we have taken from dynamic and the static graphs. And we applied these strategies to 100 static and dynamic graph simulation to find the comparison, like how they are working, how they are performing, what is the difference between the dynamic graph generated strategies and the static graph generated strategies, or which is more efficient. So this table we can see, this is actually when the simulation were applied to 100 static graphs. As we told earlier that we particularly focused on the maximum infected and the total infected matrix. So based on that, we see that there is one strategy we found that is like D6, which performed well both in regard of the maximum infected and the total infected people. The number is less than all other matrices here. And this is same like for the dynamic graphs, we have performed 100 simulation for the dynamic graphs. And here also we have seen that the same algorithm that performed well here as well. So now let us have a look on this dynamic 6 algorithm, which is like, this is actually an algorithm which is quite difficult to understand from here, but what actually it means that we should vaccinate the individual considering the importance of the graph centrality measure. That means if one node or one particular individual, he is connected to some person or he has connection to person who is already infected, so we should consider that individual also as a critical node and we should vaccinate that person. And eventually we should vaccinate more individual eventually, because we know that as time passes by, there is a chance of getting the infection to more people. And there are some other significant strategies we have came up with, degree, when an individual degree will be greater than the average neighbor degree, we should vaccinate that, which actually mean that we should also vaccinate the relatively high degree individuals. What that means is, suppose like a highly dense city like Toronto, there the degree, like the people who are connected with or like who is vaccinated, who has infection, that ratio will be something different if we consider like the city like Antigonish, because we know that Toronto is more dense like than Antigonish. So what that means that we should always, like, even though no matter it is not like, even though like for small cities also, if that is we found that it is greater than average degrees, we should vaccinate that people also. We should not consider that like it is lower than the people staying in Toronto. We should, when we are considering about some particular town or city, we should consider that relative high degree here. So after that, we also tried to make a comparative analysis between the base strategies and the dynamic strategies, and some baseline strategies were also comparing. So we have seen that the base strategies have always been performing the worst. And while we consider the maximum infected matrices, we found that the static graph generated strategies were more like good, performed good in, but while we considered the total infected strategies, the dynamic graph generated strategies were performing well. And also we can see that some large probability values we found while we were comparing the static and dynamic graph generated strategies, which actually means that there is relatively a very small difference between the efficacy on the static graph generated strategies and the dynamic graph generated strategies. And these four values, like four pictures, they are actually showing the probability value comparison for the individual strategy level. And here also, interestingly, we have found that the similarity for the metrics between the dynamic and the static simulation were almost similar, which also implies that like maybe there is very less significant difference between the dynamic and the static graph generated strategies. So we actually built an algorithm system for developing the vaccination strategies on a dynamic graph, and we tested the system on multiple dynamic and strategy graph simulation for understanding the efficacy of our strategies. And also we made a comparison to see how these strategies like they're evolving while the static graph simulation is changing. So we came up with a solution that we haven't, even though we saw that like the dynamic 6 algorithm was performing well, but actually we can say like there is no silver bullet strategy we have found so far. And also we have seen that the more significant differences we found when we considered the individual strategies than between the group. So which actually implies that these evolving strategies that is like causing because of the dynamic simulation of the graphs, they may not be as important as we thought. So we can actually simplify the complexion of the problem. So what that means that if we like for finding an effective vaccination strategy, even though we consider a static graph also, the strategies the graph simulation will come up with, they also might be like as efficient as these static graph, dynamic graph generated strategies are. So this is all, like, thank you. And if you have any question, I'm happy to answer.